Indeterminate products. If the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to infinity, or negative infinity, then it isn't clear what the value of the limit as x approaches a of f of x times g of x, if any, then it will be. Now, there is a struggle between f and g, so if f wins, the limit will be 0. If g wins, the answer will be infinity or negative infinity. Or there may be a compromise where the answer is a finite non-zero number. This kind of limit is called an indeterminate form of the type of 0 times infinity. Now, we can deal with it by rewriting the product f times g as a quotient. So f times g is equal to f over 1 over g, or we can say that f times g is equal to g over 1 over f. Now this converts the given limit into an indeterminate form of type 0 over 0 or infinity over infinity, so that we can use L'Hopital's rule. So for example 6, we want to evaluate the limit as x approaches 0 from the right of x times the natural log of x. We're going to use the knowledge of this limit together with the information from derivatives to sketch the curve of y is equal to x times the natural log of x. Okay, so first, when we take a look at this limit, if we have the limit as x is approaching 0 from the right, and we have x times the natural log of x, well then what that does is that gives us 0 times negative infinity. Because if we look at the graph of the natural log of x, which is here, this is the natural log of x, as it is approaching 0 from the right, it's approaching negative infinity. Okay, so this is the natural log of x. Okay. So now we determine that this kind of limit is called an indeterminate form of the type 0 times infinity. So we're going to have to deal it by writing the product f times g as a quotient. So we can either use this form or the second form. Well, we have x and then we have the natural log of x. So we're going to use this form, okay, where we're going to let f represent x and we'll let g be the natural log of x. So now we're going to write this as the limit as x is approaching 0 from the right of the natural log of x divided by 1 over x. Okay, so now what this tells us is now this is going to negative infinity, and we know that this is going to go to negative infinity. So now what we're going to do is now we're going to take the derivative of the numerator and denominator by using L'Hopital's rule. But before we do, let's just go ahead and rewrite this. So we have x approaching 0 from the right of the natural log of x over x to the negative 1. So now we're going to use L'Hopital's rule. So we're going to take the derivative of the numerator and the derivative of the denominator. So the derivative of the natural log of x is 1 over x. And the derivative of x to the negative 1 is negative 1 times x to the negative 2. So if we want to rewrite this, okay, we know that the value of x to the negative 2 is going to be in the numerator, and this 1 over x now becomes x in the denominator. So therefore, by simplifying this a little further, we have x to the, as approaching 0 from the right. So 1 over x is the same thing as we have 1 over x, and then we can rewrite negative x to the negative 2 in the numerator. So that's negative x squared over x. And now we can simplify that a little further. So we have the limit as x is approaching 0 from the right of negative x. And so now what we get is when we apply this limit, we get the limit of 0. Okay? So now once we have this information, we want to be able to then put this together to sketch the curve of y is equal to x times the natural log of x. So in order to do that, we want to be able to find the first in the second derivative. So now we have the function y, which is equal to x times the natural log of x. Okay, and what we want to do is we want to find the derivative of that. So we're going to use the product rule. So the derivative of x is 1, and then we have the natural log of x. Plus, we have the derivative, or x times the derivative of the natural log of x, which is 1 over x. So therefore, we now know that y prime of x is going to equal the natural log of x plus 1. So there is the derivative of this function. Okay, now recall that we now want to be able to find the critical numbers. So in order to find the critical numbers, we need to set this first derivative equal to 0. So we have the natural log of x plus 1, and we're setting that equal to 0. So we're going to subtract 1 to both sides, so we have the natural log of x, which is equal to negative 1. Okay, so keep in mind here that we can rewrite this now in terms of an exponential form. Okay, so it's in logarithmic form. So that means that we can say that x is going to equal the base that has the exponent of negative 1, which is the same thing as 1 over e. So the critical number x is equal to 1 over e. And let's just see what that approximation is on our calculator. Okay, so we have 1 divided by e. And so there is our approximation. So let me copy that down so we can use this for reference. So we have that. And now what we want to do is now we want to test that critical number. So there is our value here. So you can see that we can round that to 0.37. Okay. So now that we have that number, just leave that right here. Okay, what we want to do is we now want to use that in our interval. So we have our interval. We know that we have 0, and the critical number is located at 0.37, or that's 1 over e. So we know that we have these two regions that it covers. Okay, so we have a region that's going from negative infinity to 1 over e. So negative infinity to 1 over e. And we have another region that goes from 1 over e to positive infinity. So now we're going to pick a value from region 1. Okay, but keep in mind here that the value from region 1, we cannot use 0. And we can also not use any negative numbers because the natural log of a negative number or 0 is undefined. So that means that we need to look at this part here. So the number in between 0 and 0.3, we can use 0.2. So we're going to let x equal 0.2, and then we're going to plug that in. So if we plug in 0.2 into the derivative function, so the natural log of 0.2 plus 1, let's see what we get. Let's go ahead and plug this into our calculator. So if we take the natural log of 0.2 and then add 1, we get negative, so it's negative 0.6. So that means that we know that the derivative here is less than 0. And then if we take a look at region number 2 and let x equal 1, so we get y prime is equal to the natural log of 1 plus 1, well, that's going to give us positive 1. So that means that we know that derivative is going to be greater than 0 in region number 2. So let's go ahead and list all the information that we have from here. So we know that f prime of x is going to be greater than 0 when x is greater than 1 over e, and we know that f prime of x is going to be less than 0 when x is less than 1 over e. Okay, and we know that f of x is going to be increasing on the interval from 1 over e to infinity. And we know that f of x is decreasing from 0 to 1 over e, because we can't look at anything below that, so we're looking at the interval here from 0 to 1 over e. Okay, so now let's find out what happens when we plug in f of 1 over e. So if we plug that into our function, our regular function, which is f of x, which is equal to x times the natural log of x, we get 1 over e times the natural log of 1 over e. And remember that 1 over e is the same thing as e to the negative 1. So that means that we get 1 over e times negative 1. So we get negative 1 over e. So that means that we have a local minimum at 1 over e, negative 1 over e. Okay, now if we wanted to write this in terms of a decimal, we know that this is 0.37 and negative 0.37. So the last thing we need to do is we need to determine whether it's concave up or concave down. So again, we know that our derivative function was the natural log of x plus 1. Now, if we want to find the second derivative of this function, it's going to be 1 over x, provided that x has to be greater than 0. Okay, so what does that tell us? Well, that tells us that this is going to be concave up on the interval from 0 to infinity. So let's take a look at this graph. So here is our graph. So this is what our function should look like. So f of x is going to equal x times the natural log of x. So down here, we can see that that represents the local minimum, which is the 1 over e, negative 1 over e. Okay, and then we also can see that it is concave up from 0 to infinity. So it is concave up from 0 to infinity. Okay, and so therefore we have a point at 0, 0, and there's our 1, 0, and therefore there is our graph. Now, in this example, there would have been another possible option, but it would have been to write the limit as x approaches 0 from the right, x times the natural log of x, which is equal to the limit as x approaches 0 from the right of x over 1 over the natural log of x, which means that we would have chosen this first one. Okay, but if we would have done that, okay, this would give an intermediate form, indeterminate form of the type 0 divided by 0. If we apply L'Hopital's rule, we get a more complicated expression than the one we started with. So in general, when we rewrite an indeterminate product, we try to choose the option that leads to the simpler limit. So having the 1 over x in the denominator gave us a better way to be able to solve the problem as opposed to using the other way.